Hello and welcome everyone. For this video lesson, we will be learning another method for computing determinants. Recall that if A is an n by n matrix with ij entry aij, then the determinant can be given in terms of the following summation. This summation runs over all the permutations in S of n, and every term is a signed product of uh, terms coming from each row without repeating column number. If we fix a coordinate ij, notice that we may separate the determinant of A, or I mean this sum, into two parts. We can separate it as a sum of two terms, where the first term is the sum of terms that has aij as a factor. The other sum is the sum of all terms without aij as a factor. So you can think of the terms here to be those that includes aij when you select from the first row to the last row. Now, because every term in the first term has aij as a factor, we can factor the uh, number aij out and have another expression over here, which we denote by capital Aij, where, again, Aij is what's left when we factor Aij out from among all the terms that contain Aij. The thing that's left when we factor out Aij, which we denote by capital Aij, is what we call as the cofactor of the entry Aij. So to recall, to get the factor of the entry Aij, we want to collect all the terms that has aij as a factor. Now, if the terms are already collected, we factor out the aij, and what's left as the other factor is called as the cofactor of little aij. The question is, how can we compute for the cofactor big aij efficiently? Well, to illustrate this definition, let me um, choose a 3 by 3 matrix. And here, we would like to know the cofactor of the entry A23, or the entry on the 2, 3 position. So here is the determinant expansion of a 3 by 3 determinant. So these terms correspond to the terms in the downward direction. And these terms represents the terms obtained from these upward line directions. All of these have minus signs before them. To get the cofactor of A23, we consider all the terms that has A23 as a factor. So these are highlighted in yellow. So here is the sum of all the terms that has A23 as a factor. When we factor out A23, what remains is what we call as the cofactor of the entry A23. Hence, we can write capital A23 as little a12 times little a31 minus little a11 times little a32. Observe that this is actually a determinant of a 2 by 2 matrix. And this determinant, if we try to interchange the first and the second column, we get the following. Why did I interchange? Because as you can see, this determinant is the determinant obtained by deleting the entries from the second row and the third column. So what remains is are these four entries forming this determinant, and it is appended by a minus sign. So in this case, we see that the cofactor of the entry A23, now A23, is a 2 by 2 determinant coming from a 3 by 3 determinant. Now, the question is, why would we want to compute for cofactors of entries? The following gives us an idea about the reason why we wanted to know the cofactor of each entry. From the n by n matrix A, I want you to pick an arbitrary row. For example, the row I. The row I of A has entries AI1, AI2, and AIN. Notice that every term of the determinant, no, has to pick a factor from these row ones. No? I mean, every term has to get a factor coming from the row I. Hence, we may separate the determinant or the terms of the determinant into n parts. No? The first part being those terms that has AI1 as a factor, those combination that passes through AI1. The second part is the sum of all terms that uses AI2 as a factor instead, and so on. And the last part is are the terms that has AIN as a factor. Notice that in each of these terms, we can factor out AI1, and what's left is the cofactor AI1. And then, in the second part, we can factor out all the factors AI2, and what's left is the cofactor of the entry AI2, and so on. The last part can be written now as AIN times the cofactor of AIN. Hence, we were able to write the determinant of A as a linear combination of cofactors. Notice that these are cofactors of the entries in an arbitrary row. Hence, we have the following theorem. If A is an n by n matrix with entries in F, then for each I from 1 to n, the determinant of A can be expressed as the following linear combination. Similarly, we can choose an arbitrary column instead. Remember, whatever we can do for the rows can also be done with the columns when in terms of determinants, right? So if you choose an arbitrary column, let's say column J, these are the entries on the J column. So you can think about the determinant as the combination or the sum of all the terms where every term chooses an element from the J column. Therefore, you can separate the terms into n parts as well. The first part being those terms that has A1j as the factor, those terms that has A2j as a factor, and those terms that has ANJ as a factor. And the following result follows. This expansion or this manner of writing the determinant is what we call as the cofactor expansion along a row, because we choose a row, an arbitrary row, and then perform the expansion. On the other hand, this manner of writing the determinant is called as the cofactor expansion along particular column, in particular along the column J. So, the question now is, how do we compute for the cofactors? If we know how to compute for these cofactors, then we can just write we can simply compute the determinant by just simply calculating this linear combination, right? So what's left to be answered is that how do we compute for the cofactor of each ij entry for all I and for all j? To answer this question, let us first answer the um, easiest case. This is when ij are both 1. In other words, we are considering the 1, 1 entry of the matrix. What are those terms? What is the cofactor of the entry A1, 1? Remember, in order to get the cofactor of the entry A1, 1, we wanted to get, no, if this is your matrix, A1n, if this is your determinant, we wanted to get all the terms that has a11 as a factor. And then, having selected a11 as the entry in the first row or first column, notice that for the rest of the factors in a term, we only need to get a factor over this region because we cannot obtain a factor from this because we cannot repeat a row or a column. You remember that? So, in order to write this properly, observe that the determinant of A can be written as the sum of the terms with a11 as a factor plus the sum of the terms without a11 as a factor. Among the terms with a11 as a factor, you can factor a11 out, and what's left is the cofactor of the entry little a11, denoted by capital A11. Here we set the set S. We set the set S as the set of all permutations in S of n that fixes 1, meaning to say these are the permutations that leaves 1 in its place. Therefore, when we use the permutations in S, when we consider the terms in the determinant that chooses a permutation pi from S, you see that this corresponds to those terms um, whose first factor is a11 because pi of 1 is 1, pi of 1 here was replaced by 1. Hence, the sum of all the terms of this form over all permutations pi and s are those terms that has a11 as a factor. If we factor out a11 among all these terms, you see that what's left is this summation. Therefore, by comparison, this summation has to be the term capital A11. But notice that every permutation in S induces a permutation in the set 2, 3, 4, and so on up to n. Because a permutation in S fixes 1 and may interchange things from 2 to n, then therefore we can think of the permutations in S to be permutations in the set 2, 3, 4, and so on up to n. Hence, the summation may be thought as the determinant of an n-1 by n-1 matrix obtained by deleting the first row and the first column of A. As you can see, this was obtained by simply deleting the row that contains A11 and the column that contains A11 from the original matrix A as claimed. So already we have a formula for the cofactor of the 1, 1 entry. Now let's consider the more general case. What if ij is not located at 1, 1? How do we compute for the cofactor of that ij entry? First, consider the matrix B obtained from A by performing the following in order. For S equals 1, for S from 1 to j minus 1, I want you to swap column j minus s plus 1 and column j minus s. So for example, when n is 1, no, we will swap column j and column j minus 1. Then when s is 2, we're going to swap column j minus 1 and column j minus 2. When s is 3, we swap column j minus 2 and column j minus 3, and so on until we reach the point where s is j minus 1. In this case, we now swap column, what's this? Column 2 and column 1. So as you can see, we are swapping two columns at a time, beginning from the j and j minus 1 columns. Notice that these are two adjacent columns, no? To the left. This one is a column to the left of j, column j. So you swap them. The moment you have swapped them, you now swap the column j minus 1 with the preceding column j minus 2, and so on, until the column j reaches the point where it is in the second column. In that case, we finally swap it with the first column. So notice that this action, as an effect, places the column j of a to the first column, no? While this not disarranging the other columns. What do I mean by this? As you can see, if I consider, for example, this matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, notice that we have three columns over here, 1, 2, and 3. So if we first swap the second and third column, we get the following as a result, right? And then, of course, these determinants are no longer equal. This one is the negative. The determinant of this is the negative of the original one. And then if you swap the second column and the first column, you see that it becomes 3, 6, 9, 1, 4, 7, 2, 5, 8. So as you can see, the new arrangement will be 3, 1, 2. The relative positions of the other columns, which are columns 1 and 2, are not changed. Versus, you might ask me, sir, why can't we just swap rows 1 and 3? So to put the third column in the first row. You can do that, but by doing that, notice that the new arrangement of the columns will be in the form 3, 2, 1. When you swap 3 and 1 right away, no, you see that it disarranges the relative position of the second and the first column, and we don't want that to happen. Okay, that's why we are doing the swapping, the column swapping one at a time. Now, the moment that the jth column reaches, the moment the jth column reaches the first column, no, it doesn't. This method does not disarrange the other columns, the relative positions of the other columns. The moment we reach that, we now do that for the rows. We wanted the row I, no, we wanted the row I of the new matrix be placed in the first row without disarranging the other rows. Just like what we did for the columns, we are doing that for the rows as well. Therefore, in effect, if you look at the ij entry on the ij position, after the steps or after these operations are performed, it will now be located in the 1, 1 position. Notice that if we count the number of column and row swaps that we did, because we want to take note of that, because the sign of the determinant changes whenever we swap a row or we swap a pair of rows or a pair of columns, right? Notice that there are j minus 1 column switches and I minus 1 row switches. Therefore, there are a total of I plus j minus 2 row and column swaps, making the matrix be as follows. So now, as you can see, the ij entry was now located in the 1, 1 position. As you can see, on the row that contains aij, the other entries are precisely the entries in the ith row, no? Where the entry aij is now placed in the first position, leaving the jth position blank. No? On the other hand, the jth column of the original matrix A is now located here, where the entry on the ith row was placed in the first position, and here nothing is left. No? Whatever is left here, how do we describe the matrix Mij? The matrix Mij is just a matrix of size n minus 1 by n minus 1 because it lacks one column and one row. And it is obtained by simply deleting row I and column j. Since the determinant of b is negative 1 raised to I plus j minus 2 times the determinant of a, why is this so? Because this is the total number of times we swap a pair of rows or a pair of columns. Therefore, we will have an extra factor of negative 1 this number of times. And because negative 1 raised to negative 2 is just 1, we can simplify this expression as negative 1 raised to I plus j times the determinant of a. So basically, if the determinant of b is different from the determinant of a, they only differ by a change in sign. Using the ij equals 1, 1 case, it follows that the cofactor aij, capital Aij, of the entry aij in the matrix A is the following. The cofactor is simply the extra factor negative 1 raised to I plus j times the determinant of the matrix obtained by deleting row I and column j. We call the matrix that remains when you delete the row I and the column j as the ij minor of the matrix A. Okay, so this gives us a formula for the cofactor of the ij entry. So this method of computing determinant is not claimed to be easier because, as you can see, we are expanding. For example, you are given a 5 by 5 matrix, or the 5 by 5 determinant no, is just going to be a linear combination of 4 by 4 determinants. But the good thing is, of these 4 by 4 determinants, you can then again use row or column cofactor expansion to make them 3 by 3. No? And each of these 3 by 3 can be expanded into a sum of 2 by 2 determinants. So that's the beauty of the cofactor expansion. But take note that the cofactor expansion is best used when the matrix has a number of 0 entries, because when an entry is 0, most of the terms in the cofactor expansion will just be 0. To illustrate what I'm saying, now let me give you an example, but before giving you an example, I have to say something about the expression negative 1 raised to I plus j. Now, if you form the matrix with entries minus 1 raised to I plus j, in the 1, 1 position, it is just 1. In the 1, 1, 2 position, because 1 plus 2 is odd, it is negative 1, and so on. As you can see, the changes in the sign are in the chessboard pattern, no? Plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, minus, and so on. This tells you that the sign, or the pattern of the sign, that this extra factor will give you. Later, this will kind of appear. So let's evaluate this determinant. As you can see, this is a 5 by 5 determinant. So at first, it looks very intimidating because it's 5 by 5. But notice that in this case, we have a column where almost all of the entries are 0 except for the for one entry. So when you look at this column, for example, this is a good place to perform the cofactor expansion. Why? Because this is just going to be 1. You pick the entry 1 times negative 1. I'm sorry. Times negative 1 raised to, what is the position of the entry 1? It's on the first row, second column. So this is 1 plus 2 times the determinant of the matrix obtained by deleting the first row and the second column. So what's left is the determinant 9, 9, 9, 9, 2, 4, 0, 5, 0, 9, 3, 9, 0, and 6, 0, 7, 0. So what's left is this determinant. Plus, supposedly we are going to add few more terms, so we are expanding along the second column, right? But the other terms will just be 0 because the entries over here are 0. So there are, lalagay ko dito, 0 times some determinant, no? Plus 0 times some determinant. Whatever that determinant is, it's just 0. Okay? So all of these are just 0. So what's left is this determinant. By the way, negative 1 raised to 1 plus 2 is negative 1. So there's a negative 1 factor over here. Now here, we are now going to select the column or the row which has the most number of zeros. In this case, as a strategy, no, we always select the rows or the column which has the most number of zero because by expanding them, it reduces the number of operations. In this case, I'm going to use the fourth column and I'm going to expand along that fourth column. So the expansion should be 2 times negative 1. What's the position of 2 in the new matrix? It's 1 plus 4 times the determinant of the matrix obtained by deleting the first row and the last column. So what remains is 4, 0, 5, 9, 3, 9, 6, 0, 7. Plus zeros, no? Plus zeros. Okay? Upon simplifying, you see that this is now, so the scalars outside the determinant is now just negative 1 times negative 1. That's just 2. Alright? And then how do we perform this determinant? So if you're not satisfied with this, you don't want to evaluate this 3 by 3 determinant using the basket weave method, no? You can even, or you can further use cofactor expansion. Here, we now select the second column. We haven't used row expansion, no? Puro column expansion. Anyway, you will see that later, maybe. Alright, so 2 times, I'm going to change color. So 0, because of the 0 entry over here, plus 3 times negative 1 raised to, what's the position of 3 in this matrix? 2, 2, 2. Determinant of the matrix obtained by deleting this. So you get 4, 5, 6, 7, then plus 0. So at this point, we can now evaluate this easily because we now just have a 2 by 2 determinant. So this is 2 times 3 times 1 times 28 minus 30. It's like the usual. Ganon. Okay? So that's 2 times 3 times 1 times negative 2. That is, I think, negative 12. So the determinant is negative 12. How about this matrix? So this is a 4 by 4 determinant. So normally, again, we look for the column or the row which has the most number of zeros. In this case, the second row has the most number of zeros. But I did not tell you to use the cofactor expansion method only, no? You can make the calculation more efficient when you try to combine methods studied in the past lesson. For example, if a matrix has no no rows with many zeros, you can create zeros, right? By elimination. So, as for me, when I evaluate determinants using this method, I always look for an entry 1 anywhere in the matrix. And then, using that one, I'm going to eliminate by either row or column, what do you call this? Row or column elimination, no? All the entries adjacent to it. So for example, I will show you what I'm talking about. So I saw that this row has the most number of zeros. So what I do is I'm going to use this 1 as a pivot to further eliminate the 2 there. This is 0 already, this is 0 already, so that's fine. So when we eliminate, remember, when we eliminate, we are using a type 3 operation. It has no effect on the determinant. No? So here, because the pivot is in the, we're going to do it in columns, because the pivot is in the third column and the one we are going to eliminate is in the first column, we use an elementary column operation instead. That operation will be E1, 3, negative 2, but let me place here a C to denote that I'm doing it in columns. No? All right. So let me illustrate that. So the first column will be changed. We will multiply negative 2 on the third column, and then add it to the first column. So it's like negative 2 times 3, that's negative 6 plus 2, negative 4. I think that's right, no? Yeah. So can you tell me if I did an error, commit an error? 0, because that's what we wanted to do really. Next, negative 2 times 3, negative 6 plus 6. It happened to be 0 as well, right? And then, negative 2 times negative 2, that's 4, plus negative 7, that's negative 3. So, done. We are now ready to perform column or a row operation on the second column. Now, if we did not do this and you expand along the second column, you see that this reduces to a sum of two 3 by 3 determinants. But in this case, this will reduce to a 1 3 by 3 determinant. Now, by expanding along the second row. Let's now expand along the second row. So the expansion should be a 0 plus 0 plus 1 times the position of 1 that's found in 2, 3 position. The determinant of the matrix obtained by deleting this, get negative 4, negative 1, 5, 0, 1, 4, negative 3, 3, 8. Oh my god, I forgot to change the color. Anyway, plus 0. So now we have a a 3 by 3 determinant, and it can be written now as negative. So let me just rewrite the determinant over here. Now, we again look for a column or a row with the most number of zeros. Or maybe you can just kind of find a 1, an entry 1, which you can use to eliminate the rest of the entries in the column or in the row. So in our case, I will select this one. Now what if you cannot find a 1? Well, you can make a 1 by performing a type 2 operation, but you have to take note that the determinant changes whenever you perform a type 2 operation. Alright? Alright, so I'm going to use this one and eliminate the 4. So here I'm going to use a column operation once again. The one to be eliminated is in the fourth column. The pivot in the third column. The pivot is in the second column, and I'm going to use minus 4 as an eliminating factor. The determinant will not be changed essentially. Alright. 0. I'm sorry. I'm going to write the first and the second column first, because the last column will be changed. No? So, ganito yan. Negative 4 times negative 1, that's 4 plus 5, that's going to be a 9. I think so. If I am wrong, maybe you can call my attention. Next, negative 4 times 1 plus 4, of course, that's 0. That's what we wanted to do, really. Next, negative 4 times 3, negative 12, plus 8, that's negative 4. Wonderful. So we now are going to expand along the second row. Expanding along the second row, we get 0 plus 1 times negative 1 raised to 2 plus 2. Determinant of the matrix obtained by deleting this, so you get negative 4, 9, negative 3, negative 4. Alright, plus 0. Finally, because this is just a 2 by 2 determinant, we can now do it by hand. So this is just going to be the determinant minus 4, 9, minus 3, negative 4. That is 16 minus negative 27. So I guess the answer is 43. Is that 43? I don't know, maybe you can check using your softwares to check whether the answer is 43. If not, you can maybe find the error or the mistake that I did. I hope this is correct. Another exercise. Suppose you're given that the 2 by 2 determinant A, B, C, D is equal to 5. I want you to calculate the 4 by 4 determinant as shown using this information. As you can see, every column and every row has 2 0 entries, right? So we can expand along any row or any column. It won't matter. For example, if I expand along the first row na lang, so I have two non-zero terms. The first term being a times minus 1 raised to 1 plus 1 because that's in the 1, 1, 1 position. Eliminate the first row in the first column, you get a, b, 0, c, d, 0, 0, 0, d. Where did I get this? I get it from deleting this. Plus 0 plus 0, I don't need to write that, plus b times negative 1 raised to, b is in the 1, 4 position, determinant of, eliminate this and that, you get 0, ab, 0, cd, c, 0, 0. Alright. Now this one is just a. Now for this term, we can get another cofactor expansion, let's say along the last column, 0, 0, d. If we do it, it becomes d times negative 1. D is in the 3, 3 position, and then eliminate the column and row containing D. You get A, B, C, D. So these are 0, so we don't care about them. This is minus because, that's minus B because 1 plus 4 is odd. So here we now expand along the first column if you want. Okay? So in that expansion, we only have one term, C, times negative 1 raised to 3 plus 1 times the determinant A, B, C, D. Because we're eliminating this. Alright, I think we're done. So you can see this is just AD times 5 because this determinant is equal to 5 minus what's this? Minus BC times again 5. So this is 5 times AD minus BC. But as you can see, AD minus BC is also, as you may have recognized, this is also the determinant ABCD, which is 5 times 5. So the final answer is 25. I hope you were able to follow that. You can always rewind no, if you miss out anything. Now recall that for I and j, for all I and for all j, we can expand the determinant of A using along the any row. In this case, row I. This is what we call the cofactor expansion along the row I. Or you can even expand along any column. So this is the cofactor expansion along column J. I want you to fix an I, and I want you to select another R different from I. So it's like you have a fixed row I, and then you're going to select any row that is different from the row I. Suppose that A is a matrix, an n by n matrix where, so what does this equation mean? This equation means the row R of A, this represents all the row R because J runs from 1 to n. This represents all of the row R, A. So the row R of A is equal to the row I of J. So imagine that you have a matrix A where the row R simply copies whatever is in the row I. And of course, because this is a matrix with two identical rows, its determinant is equal to 0. But when you try to use the row R, no, to expand the determinant of A, which is by the way 0, so this is the cofactor expansion of what they call this? The cofactor expansion of R and of the determinant using the row R. But because of this condition, AR1 is equal to AI1. AR2 is equal to AR2 is equal to AI2 and so on. So I can replace this by the following. As you can see, this is a dot product of two vectors. No? The first vector is AI1, AI2, AIN. The other vector is AR1, AR2, ARN. So that's a dot product. And this dot product is 0. Alright? Alright. So this happens when R is not equal to I. But of course, if R is equal to I, as you can see, it just reduces to this expansion. It's just equal to the determinant of A, whatever is the determinant of A. We then have the following lemma, because we're going to prove something. Okay? We establish the following lemma. So this summation represents the dot product illustrated over here. Now, if we do this dot product AI1, AR1, AI2, AR2, and so on. Now, this dot product is 0 according to our computation whenever R is not I. But when R is equal to I, this just reduces to the simple determinant of A. And this must happen similarly when we try to select a particular column. If C is a column number different from J, this dot product is equal to 0, and if it's equal to J, it reduces to the determinant because of the column cofactor expansion. Okay, remember this? Because we're going to use this computation in the following. Now at this point, we would like to recall non-singular matrices. You know that non-singular matrices are square matrices which has multiplicative inverse. Ito yung mga may inverses. We know for a fact that non-singular matrices are those determinants, are precisely those matrices whose determinants are not equal to 0. Now, remember that although the determinant can determine whether a matrix is non-singular, no, still when you want to get the inverse of the matrix, you still have to work with the RREF method. No, you have to append an identity matrix on the right and then try to reduce it in RREF and see how the matrix transforms in order to get the inverse. In other words, we don't have an explicit formula for the inverse of a matrix. In fact, that's the next thing that we wanted to do. We wanted to give well, um, an explicit formula or a direct formula that calculates the inverse of a matrix. Isn't it amazing? Now, again, let capital Aij denote the cofactor of little aij. If we take the dot product of row I of A and column J of Aij transpose, what is this? So let me first explain. Here, remember when we do the transpose, the first row should be the first column. The second row should be the second column of this, and so on. Huh? So what we mean by Aij transpose for your information, this is a transpose of a matrix. This is a new matrix different from the original matrix, no? The first row, this is the second row. Okay. This is the nth row. And then we don't stop there, we take the transpose. The transpose should then be A11, A12. The first row will now be written as columns. First column. The second row will now be the second column. Of course, the last row will be the last column. Alright. So this is what we are referring to. So basically, this is just the matrix that contains all the cofactors transposed. We take the transpose. Now, what is happening here? So we are taking the row I of A, the original A with entries little aij, with the column J of this matrix. What's the column J of this? Ang column J niyan will be AJ1, AJ2, di ba? AJN. So if we take the dot product of the row I, so these are the entries from the row I of A, and these are the entries from the column J of Aij transpose. So if we take the dot product, you see from the lemma that this is just 0 whenever I is not J, and it's equal to the determinant of A whenever I is equal to J. Hence, we have the following calculation. Oh, something nice happened about this. Now, this is the original matrix A. For your information, this is the original A. This is the matrix of cofactors transposed. Now, for example, why is this equal to that A? Because to get this, you need the first row and first column and then take the dot. But when you take the dot, that is nothing but the cofactor expansion of A along the first row. So that's that A. But if you take, for example, the first row and the second column, you get A11, no? For example, A11, A21, if you take this and this, plus A12, A22, A1N, ANN, A2N. As you can see, because the first coordinates differ, right? They differ according to the lemma that is just 0. So whenever I is different from J, you only get zeros. In other words, off the main diagonal, you get zeros. But on the main diagonal, you get that A. So as you can see, you get a diagonal matrix with that A, the determinant of A, being the main diagonal entries. We call this matrix Aij transpose as the adjugate of A, for it to have a name. And this adjugate is denoted by adj A. Now some authors, adj A some authors call this the adjoint of A, but I don't like to use the adjoint because in linear algebra the word adjoint has a more important meaning other than this, no? So I would like to use the adjugate instead of the adjoint. So this matrix is called the adjugate or the adjoint of A, denoted by adj A. And we have formulated the following theorem. We call this the adjugate theorem. It says that if you multiply the matrix with its adjugate, you get a diagonal matrix with diagonal entries reflecting the determinant of A. So that's the determinant of A times the identity matrix. Alright? And even when you do it in the other direction, you will use the lemma number to get this. Okay? Now from here, we can get the formula for the inverse. Why? Kasi if A is non-zero, non-singular, I'm sorry, if A is non-singular, we know that its determinant is not 0, right? So this number over here is just a scalar that is not equal to 0. Therefore, I can multiply this equation in every side, no? I can multiply that by the reciprocal of the determinant of A. And when I do so, yung 1 over, yung scalar na 1 over that A can, of course, be just placed over here. I can just place it over here. This is just a scalar, no? What's left in the middle is just the identity. Similarly, 1 over that A, A, times A is equal to the identity. Therefore, whatever this matrix is, this is the matrix that you need to be multiplied to A to get the identity. Therefore, this is precisely the inverse. So how do you get the inverse? You get the adjugate matrix. Now divide after getting the adjugate matrix. How do you get the adjugate matrix? You get the matrix containing all the cofactors only. And then divide every entry by, this is just entry-wise division. You just divide every entry by the determinant of A. Alright? For example, let's talk about this matrix. Let's calculate the matrix adjugate of A. To calculate the adjugate of this matrix, we simply calculate all the cofactors of each entry and then arrange them in a matrix relative to this position and then take the transpose. So this is what I'm going to do. The cofactors of the entries in the first column will be placed in the first, the cofactors of the entries in the first row, I will place them in the first column so that where they are arranged in order. Alright? So for example, what's the cofactor of the 1, 1 entry 2? That's negative 1 raised to 1 plus 1. I'll delete this. You get the matrix 1, 0, minus 2, 3. And when you try to calculate this one, you get, what's this? This is 3, right? Next, 1, 2. But as you can see, the cofactor of the 1, 2 entry was placed below A1, 1B, so that these are already arranged. No? So you're just going to place them in a matrix. A1, 2 is negative 1 raised to 1 plus 2 times, eliminate this one, we get 1, 0, 0, 3. So that's 3. What's that? 3 times negative 1, that's negative 3. A1, 3 is negative 1 raised to 1 plus 3. 1, 3 entry is this. So you get 1, 1, 0, negative 2. So I think this is negative 2 times 1, negative 2. I'm going to now get the cofactors of the entries in the second row. So I'm going to place them in the second column. So 1, that's negative 1 raised to 2 plus 1. I delete this. Okay. You get 0 minus 1 minus 2, 3. So what's the answer for this? The answer is, I think this is negative 2 times negative 1, that's 2. A2, 2, negative 1 raised to 2 plus 2, determinant of this matrix, 2 negative 4 corners. Alright, so I get 6 times 1, that's 6, A2, 3. So as you can see, this is a very tedious operation. 2 plus 3. So we are over here. Delete this. 2, 0, 0 minus 2. So I get negative 4 times negative 1. That's 4. Alright, so we are now on the last row. You can imagine that you're doing this for a 10 by 10 matrix. This is kind of tedious, right? But it's not a very good method or a very fast method, but it is a method. So A3, 1. 3 plus 1, so I'm going to eliminate this. I get 0 minus 1, 1, 0. So I get negative 1 times 1, negative 1. Oh, I'm sorry. 0 minus negative 1 is 1. That's a 1. A3, 2. Alright. A3, 2. What's A3, 2? Negative 1 raised to 3 plus 2. Sorry. Times. I did a mistake over here. This is times the determinant. You eliminate this, you get 2 minus 1, 1, 0. So the determinant is 1 times negative 1, that's negative 1. Okay. If you're having difficulty, you can pause and then kind of do this on your own and check if our answers match. Negative 1, 3 plus 3. You finally eliminate this one, you get 2, 0, 1, 1. This determinant is just 2 times 1. That is 2. So, what is now the what is now the matrix adjugate? So, well, we just copy these entries, no, in this order. So you get let me place it here. Let's say adj A. Sorry. So therefore, adj A. If our calculations are right, adj A is, so let me copy row by row, 3, 2, 1. And then negative 3, 6, negative 1. And then negative 2, 4, 2. Okay? So I think this is the adjoint of A. Next, we're going to calculate the inverse of A whenever it exists. So first, we need to get the determinant. But do you remember this identity from the previous theorem? Right? So you can actually get the determinant by multiplying A and its adjoint. If you multiply A and its adjugate or adjoint, so we can do it by hand. But basically, we're doing the following. I hope this leads to a diagonal matrix, otherwise something is wrong in our calculation. Alright, so let me do the calculation for you. There, so as you can see, I have done the multiplication for you and I get 8 times the identity. This indicates that the determinant of A is precisely 8. Well, you can check if you want. But according to the theorem, the determinant must be 8. And therefore, because this is not 0, A is non-singular. And we now have a formula for the inverse of A. That's just 1/8 of the adjugate. It's just going to be 1/8 of the adjugate matrix. just as shown, right? Because if you take 1/8 of these entries and you get to multiply it to 8 to A, you now get the identity as a result. So this is the inverse. In fact, the inverse, if you want to express this in terms of fractions, no, you can write it this way. But for me, I don't like writing these fractions. I am just okay with writing 1/8 outside. 6/8 is fine with me. If you want to simplify, you may. For me, I don't like to simplify because I want to see what is the determinant. So that's the inverse of A. Alright? So I think we are now in the last portion of this lesson. And this is where you will see the power of the cofactor expansion because we're going to use this to solve linear systems when the coefficient matrix is a non-singular matrix. So let's say A is non-singular, and we are considering to solve the linear system AX equals B, where A, X, and B are as shown. So as always, this is going to be the column or the vector of unknowns. Now we all know that X can be calculated, the vector X of unknowns can be calculated by multiplying the inverse of A times B. But according to our previous theorem, the inverse of A is 1 over the determinant of A, this is scalar, times the adjugate matrix times B, because B is multiplied on the right. So we can write X, the unknown vector, as follows. 1 over that A, this is scalar, this is the adjugate matrix, and this is B. Now, as you can see, we now have a formula for each of these xi's. Now, for example, how do you get x sub 1? X sub 1 is this row dot this column. We will take the dot of this row and this column and then divide that by the determinant of A. X sub 2 should be the dot of this row and this column and then divide that by that A, and so on. In fact, for j equals 1 to n, we now have a formula for x sub j, and it's going to be b1 a1j, b2 a2j, bn an_j. This was obtained, ito yung, what do you call this? The jth row of the adjugate, but of course this is the only column of b, divided by that a. Now, for each of the values of j, what do you think is the numerator? That's what we wanted to know. So this is what we do in order to understand the numerator. For each j, no, I want you to define or consider the matrix J. What is this? Basically, this is just the matrix A, no, where the jth column is replaced by B. So how do we describe AJ? AJ is just the matrix A where the jth column was replaced by the column B. So this is now the column B placed in the jth column position of the original matrix A. If we try to evaluate the determinant of AJ and expand it along this column, you see that the cofactor expansion is just B1 times the cofactor A1J, right? Plus B2 times the cofactor of A2J. A2J here is B2, right? Plus and so on, B sub n times the cofactor of A and J. And that turns out to be the numerator of x sub j. Hence, x sub j now has the formula determinant of aij divided by the determinant of a. We now express this result in the following theorem. And this theorem is what we call as the Cramer's rule for solving linear system, non-singular linear system. Non-singular meaning the coefficient matrix is a non-singular matrix. How do you know that it's non-singular? Get the determinant? No? Alright. So here, you get ax equals b. To get the value of x sub 1, for example, you divide the determinant of a sub capital A1 divided by the determinant of A. You want to know x sub 2, you divide the determinant of capital A2 divided by the determinant of A. Again, how do you get the capital AJ? It's the matrix obtained from A by replacing the jth column by the column B. Well, to illustrate this, just a quick example. So we wanted to have a small linear system. So we don't want to um, spoil this video and become very long. No? So for example, here, you can take A to be the coefficient matrix 2, 3, 1, 2. X be the column vector x1, x2, and B be the column vector 2, 0. Okay, so we're going to use the Cramer's rule to solve this linear system. The first thing you may need to know is the determinant of A, because this will tell us whether the Cramer's rule can be used in the first place. Remember, the Cramer's rule can only be used whenever A is non-singular. So the determinant of A is 4 minus 3, that's 1, and this is not 0, by the way. Therefore, A is non-singular. So Cramer can be applied. Okay? So, for example, how do we get x1? To get x1, we need to get the determinant of a1. What's a1? a1 is just A, where the first column will be replaced by B. So it's going to be 2, 0, 3, 2. Alright? So a1, the determinant of a1 should be 4 minus 0, that's 4. Which means that x sub 1 is the determinant of a1 divided by the determinant of A. So that's going to be 4 over 1 or 4. So there you get the value for x1. The determinant of A2 now A2 is going to be the matrix obtained from A by replacing the second column by B. So you copy the first column of A, you replace the second column by B. And this determinant happens to be 0 minus 2, that's negative 2, right? So x sub 2 is that A2 divided by that A. But that is just negative 2 over 1, so that's negative 2. So you finally get the value of x sub 1 and x sub 2. So solution, you get the following solution. Only one solution, of course, because the linear system is non-singular. Okay, if we want to check if this solution is correct, you just simply substitute. For example, when x1 is 4, this is 8. x2 is negative 2, this is minus 6. 8 minus 6 is 2. Check. 4 minus 4 is 0. Again, check. So these solutions are correct. So if you have questions, you can send me an email, or you keep a record of your questions, and when we do the live sessions, you can ask them. Okay? Next lesson will be a new chapter, and we will be talking about vector spaces. Right? See you next time.